Okay, thank you very much, Jesus. So I'm going to talk about recent calculations about lithium 11 plus P and lithium 11 plus D. It's essentially about elastic scattering. And the main idea is to use a common framework for both reactions. With common framework, I mean the same lithium 11 wave functions and the same optical potentials. So the outline of my talk is here. So I will first be talking about the structure of lithium 11 and more specifically about E1 distribution. Then I will give a brief overview of the CDCC, which stands for Continuum Discretized Coupled Channel. And I will emphasize on system, which I call 3+1, which means 3 body plus 1. This is lithium 11 plus P. And 3+2, which means 3 body plus 2 body, which is lithium 11 plus D. Then I will say a few words about the air matrix method, which I use to solve the coupled channel system. And then I will come to the results, lithium 11P and lithium 11D. So this has been accepted very recently at PhysRef. So there are two experimental papers on lithium 11P and lithium 11D, essentially on elastic and inelastic scattering. So lithium 11 plus P has been measured at 66 MeV, which corresponds to a rather low center of mass energy, about 5.5 MeV. And the main conclusion of this paper is the existence of a dipole resonance at low energies, 0.8 MeV with about 1 MeV width. The other paper about lithium 11 plus D has been done more or less at the same laboratory energy. And they also concluded on dipole resonance at low energies with slightly different parameters. And one of the main results is that the E1 transition from the ground state to this dipole state may have an isoscalar character. Let's look at the E1 operator. As you know, at the long wavelength approximation, the E1 operator is written like this. When the sum includes all nucleons, this is an isospin term, which is 0 for neutrons and 1 for protons. And the first term corresponds to the isoscalar component, which at that long wavelength approximation is exactly 0, because the sum here over the nucleons is the definition of the center of mass, so it's exactly 0. This is called isoscalar. The other term is the isovector. And if you go beyond the long wavelength approximation, then there are additional terms. And the first term in this expansion is written here. So you have K gamma here, the photon wave number, and R prime, which is Ri minus Rcm. So if you go beyond the long wavelength approximation, you may have isoscalar transitions. Okay, so my work is divided in, well, let's say 3 parts. One is about spectroscopy of lithium 11. And in fact, most of that part was done in that paper by Edna Pinilla, which was published a few years ago. But what I've extended here is the E1 distribution. And I've looked at this possibility of isoscalar transition. And then the idea is to use the same formalism, I mean the same Hamiltonian for lithium 11, to 2 reactions, so one lithium 11 plus P. So this is a 4-body model. This was also considered by Matsumoto and co-workers, but in slightly different conditions. And then I also apply the same lithium-11 wave functions to lithium-11 plus D. So here it's a 5-body CDCC problem, which, as I will show you later, includes many channels. So let's start with the structure of lithium-11. So this is described in the hyperspherical model. And of course, there are many theoretical works on lithium-11, but I'm using here the conditions which are explained in this paper, PhysRef 2012. So there is a neutron-neutron interaction, which is taken as the Minnesota potential. And there is a lithium-9 plus neutron potential, which is taken as the Woods-Axon fitted on the scattering length. So this is taken from the literature. As is usual, the spin of the core is neglected. And in this interaction, lithium-9 plus neutron, there are forbidden states for L equals 0 and for P3 half, and these are removed by a supersymmetric transformation of the potential. So for 0 plus, there is a bound state as we expect, and in fact, the binding energy is reproduced by scaling factor on the lithium-9 plus neutron potential. It's very close to 1. It's 1 and a few %. And then the root mean square radius is 3.12, which is in good agreement with experiment. And here is the three-body phase shift, which I took from the reference here. So this is lithium-9 plus N for 1 minus. And as you see, there is a resonant structure here around 0.6 MeV with a width of a few hundred keV. So ECM in this diagram is the energy with respect to the lithium-9 plus to neutron threshold. So then I computed the E1 transitions, and this is the definition of the B1 from initial state to final state. So here the initial is the 0 plus ground state, and the final is the 1 minus. So there are two options for the E1 operator. E1, I use the long wavelength approximation, which means that isoscalar is 0. Or if I go beyond the long wavelength approximation, then there is a possibility to have an isoscalar contribution. And this is the E1 distribution. So as a function of the center of mass energy in lithium-11. So as we may expect from the phase shift, there is a peak around 0.6 MeV, which is here. So of course, this is consistent with the phase shift. And there are two curves here in dashed and dotted. So the dotted is the pure isovector, and the dashed is the isoscalar. And as you can see, this isoscalar contribution is quite small. It has been multiplied by 1,000. And this can be understood rather easily. There is correction by a term which is proportional to this factor. And for lithium-11 and other halo nuclei, the radius is large. So this R may be expected to be large, but K gamma, which is defined here, is quite small. And then this factor is much lower than 1. So the red curve is what I obtain with the full E1 operator. And then, as you can see, this is almost a pure isovector. So the theory does not agree with this isoscalar transition. So let me come now to the scattering problem, and I start with a brief overview of the CDCC, which is a continuum discretized coupled channel. This is a well-known method which has been introduced in the 70s, essentially to describe the deuteron breakup, we know that the binding energy of the deuteron is low, so we expect the breakup to be important. And this is the three-body equation for this problem. You have an internal Hamiltonian for the projectile, which here is a two-body projectile, then a relative kinetic energy, and two optical potential between the fragments and the target. So in general, the data obtained at rather high energies, which are far above the resonance region. And then the breakup of the projectile is described by a discretized continuum. So first, we solve the Schrödinger equation for the projectile. And I take here an example for the deuteron. It's a well-known example. So this is the spectrum of the P plus N problem, including the ground state, 2.2 MeV, which is a physical state and which does not depend on the basis. And then you have many states here which does not have physical meaning and do depend on the basis. So their role is to simulate the breakup effect of the deuteron. And then it turned out that this model was well adapted to exotic nuclei, which have a low binding energy. So we expect breakup effects to be important. And a typical example is beryllium-11, which is bound by 0.5 MeV. And I should say that this model does not require that to have a low breakup threshold. You can apply with strongly bound nuclei, but of course you expect the breakup effects to be more important if the breakup threshold is low. And then over the years, there were different extensions of this CDCC method. And one extension is to use three-body projectiles. And you have here two of the first references on this extension. This is typical for helium-6 or lithium-11 or beryllium-9. Then there were works on A-body descriptions of the projectile, for example, lithium-7 or helium-6. And the advantage of this is that it's based on nucleon targets potential. So there is no need of optical potentials between the fragments. There is no parameter here. And then more recently, I extended the CDCC formalism to systems involving two-body projectiles and two-body targets. And a typical example is beryllium-11 plus D. So, you know, there are many recent data with deuteron as a target. So if the projectile has a low breakup threshold, it's important to have extension of this CDCC method. The problem here is that you have pseudo-states in the projectile and in the target. So this means that the total number of channels is the product of these two numbers. So you may end up with rather a large number of channels. And well, this is explained in these two references. So the CDCC equations for these two systems are shown here. You start from Hamiltonian, 4-body or 5-body. Of course, this H2 here, which is associated with the deuteron, is 0 in the case of the proton. So as usual, you have kinetic energy, and then you have the various optical potentials between the different constituents. And then you use the standard CDCC procedure. And the procedure is here. You first solve the Schrödinger equation for lithium-11. in the hyperspherical method than for the deuteron. So these are rather simple things which were done in the past. So these functions here I've expanded on a basis, and I'm using Lagrange functions. I will say a bit more about Lagrange functions in the next slide. And then, as usual, you have states with a negative energy, which correspond to physical states. And in many cases, there is only one physical state. And then positive energies, which are called pseudostates, and which correspond to approximations of the continuum in the projectile and the target. And then when you have these internal wave functions, which are here for lithium 11 and deuteron, then you define channel functions here. So you have the coupling of the two angular momentum, J1, J2, are the spins associated with lithium 11 and deuteron. And I is the channel spin, and L is the angular momentum. And then you expand the total wave functions over these channel functions. And here you see, which only depends on the relative coordinates, is to be determined. And then the final, not the final step, but the next step is to compute the coupling potential, which are the matrix element of the potentials between these channel functions. And these are rather complicated calculations. There are numerical integrals and analytical integrals. And also for those who are familiar with hyperspherical coordinates, also use the Renal-Revaille coefficients to speed up the calculations. And then you end up with a standard coupled channel system, which is written here. So this is a general form, which is common to most scattering theories. So here you have these coupling potentials. And at large distances, when you have only Coulomb, you know that the relative wave functions only depends on the Coulomb interaction. So this is a combination of incoming and outgoing Coulomb function. And what is here is called the scattering matrix. This is from the scattering matrix that you can determine the cross sections. And in my case, I solve this system with the air matrix method, and I will briefly show how it works. Of course, this system must be solved for each j pi, and in the scattering cross-section, you may have many j pi values depending on the energy, and you may have many channels. So I remind you that C here stands for the pseudostates, but also for the channel spin, the angular momentum. So when you include everything, in the maximum for lithium 11 plus D, I have something like 9,000 values for C. So this is a really big system, which takes a lot of computer time. Another problem is that in some cases, at least, you may have a long range of the potential, essentially due Coulomb. The Coulomb coupling may be important up to large distances. So at the end, you are dealing with long calculations, and you need many tests to check the stability. And finally, when you have the scattering matrix, you determine the cross-section, which is standard. Then a few technical words. One about the air matrix method. So this is how I solve the coupled channel system. It's not the Numerov algorithm, it's the air matrix. And this air matrix is based on two regions. There is a channel radius A, and well, the main reference about the air matrix is this famous paper by Lane and Thomas, And then with Daniel B, we wrote more modern version of the R matrix. And in 2016, I published a subroutine that you can use and adapt to your own code. So the idea of the R matrix method is to divide the space into regions divided by the channel radius A. And in the internal region, you have to consider the full Hamiltonian, and you expand the wave function over a basis. And so you have n functions. A typical number is 40, 50. And in fact, you can choose any basis function, for example, Gaussian functions or sine functions. Here I'm using Lagrange functions, and I will show you in the next slides what is the advantage of Lagrange functions. And in the external region, you have to choose the channel radius large enough to make sure that there is only the monopole part of the Coulomb interaction, so the standard here. And then the external form of the wave function is this linear combination of Coulomb functions. So I skip the technical details. I refer to these references here. But the main ingredient are the matrix element of the coupling potentials. So the coupling potentials that I mentioned in the slide before. So you need a fast method to compute this matrix element. And when you match the internal and external solution at the channel radius, you can determine the scattering matrix, which is here, and the coefficients of the internal wave functions. And then you determine the cross sections. And I should say that this channel radius is not a parameter. At the end, the calculation should be stable with modification of this channel radius. And in fact, the optimal choice is a compromise. If it's too small, then you are not in these conditions. You may have high order term. But if it's too large, then you need many basis functions here, and then the computer time increases. So the best choice results from a compromise, and you have to make sure that the cross-section is stable. So one word about the basis function. So I use Lagrange functions, and this was reviewed by Daniel B in this reference. And this is based on the Gauss approximation of an integral. So you know that if you integrate a function from 0 to a, you can approximate by this finite sum. So n is the order of the Gauss approximation, and the xk are the roots of an orthogonal polynomial. So in that case, this is a Legendre polynomial. But you may have other intervals, for example, from 0 to infinity, and then you use Laguerre polynomial. And the lambda k here are the standard weights of the integral. And now Lagrange functions, which are defined from 0 to 1, but you can just scale to 0 to a. These Lagrange functions are defined by this expression. So this is Legendre polynomial divided by x minus xi. So these xi are the roots of these polynomials. And the factor here is chosen in such a way that you have the Lagrange property. So at the mesh points, the function takes this value, so the weight to the power minus 1/2. So now the nice advantage of this basis is with the matrix element. So if you use the Gauss approximation to compute the matrix element, then you find very simple solutions. First, let's consider the overlap. So the overlap is defined exactly by this integral. And if you use now the Gauss approximation for this integral, you easily find a delta ij. So they are orthogonal. For the kinetic energy, there are analytical calculations. So this can be done once. It's rather easy. If you change the potential, you don't change this matrix element. And for the potential, if you do the same thing as for the overlap, so you compute the exact integral and use the Gauss approximation for this integral, then you end up with something which is very simple. So this is the value of the potential at the mesh point, which means that there is no integral which is needed. And this is also applicable to non-local potential. And this is important to have fast calculations because these are large-scale calculations, and it's important to have fast calculation of the matrix element. So let me come to the results on lithium-11 plus P. So I use the lithium-11 description as I mentioned before. So I need two interactions, one between neutron and the target, the proton. This is the Minnesota interaction. And for lithium-9 plus P, I use the Koning-de la Roche parametrization. And to test the sensitivity, I also use the Chapel-Hill parametrization. I didn't fit anything, so I didn't rescale this optical potential. So there is no parameter. So the channel radius, well, I found that something around 25 is okay. This is not very large because the charge of the proton is 1. If you have heavy targets, for example, lead, then the Coulomb interaction is much stronger, and you have non-diagonal Coulomb terms which are important, and then you may need larger channel radii. And of course, you have to choose the lithium-11 basis. So I included pseudostates up to 10 MeV and with J max equal 3. So these are the states which are included in the basis. So the red line here is the ground state of lithium-11, and the other are pseudostates. So the first thing in CDCC calculation is to check the convergence. So this is the cross-section divided by the Rutherford cross-section as a function of the angle. And so this is with the ground state, only the ground state of lithium-11. So this is when you introduce breakup, but only with J equals 0 in lithium-11. This is J max equal 1, 2, and 3. So you can see that between 2 and 3, there is a convergence. This is why I stop at 3. And I'd like also to mention that here closed channels are important. In general, this kind of data is obtained at large energy, high energies, much higher than the Coulomb barrier. This is not the case here. So the center of mass energy is 5.5, which is lower than the maximum of the pseudostate energy. And this dotted line here is what you get when you neglect the closed channels. So if you want to have an accurate description, at least at large angles, you need to include these closed channels. And now I compare with experiments. So these are the experimental data, which I mentioned before. And this is the converged calculation with this red curve. And this black curve is the same calculation, but with another lithium-9 plus P optical potential. It comes from Chapel Hill. So the difference between these two curves is a test of the sensitivity to the optical potential. And then you may use this parametrization to compute lithium 11 plus P. This is very simple. There are parameters. Lithium 11 plus P is not included in the fit of this parametrization, but you can use the parameter, and this is what you get for the KD Kooning de la Roche potential, and this is for Chapel Hill potential. So you see that the main effect is at large angles, as we may expect. And yes, this dotted line is obtained with a smaller basis. I've shown you the basis I'm using for lithium 11 plus P, but for lithium 11 plus D, these are much bigger calculations. And I have to reduce the lithium 11 basis, and I've used a smaller basis, and this dotted line here is the result that I use, that I get for lithium 11 plus P with this smaller basis. Another interesting thing is about equivalent potentials. So the question is, can we find equivalent potentials? And to do that, you rewrite the first equation of the coupled channel system as here. So you have the diagonal term, and here you have a contribution from the other channels. So if you have, when you have solved the full system, you can compute this potential, which is called polarization potential, and which is written here. So this is exact. It provides exactly the same phase shift. But the problem is that it depends on J, and then it contains singularities, which correspond to the nodes of the wave function. You see, there are 0 here, so there are singularities for this potential. So the idea is to build a J-independent potential, and this has been suggested by Thomson's co-workers. So the polarization potential is defined by a sum over the angular momentum with a weight function. And this weight function is written here, depends on the relative distance. And this reduces the influence of the nodes, because you see, if there is a 0 here, there is no 0 in the full sum. But of course, this is not exact. So at the end, you have to verify that this polarization potential reproduces the full calculation. And so this is the equivalent potential, the real part and the imaginary part. The black curve corresponds to the CDCC equivalent potential. And I compare with the simple Kooning de la Roche lithium 11 plus P potential. And this is a zoom on the imaginary part. And as you can see, the main difference comes from the large distances. There is a range which is larger for CDCC. And this provides you with this cross-section. So the two curves here are, one is the exact CDCC calculation, and the other is the one obtained with this potential. So as you can see, this is not strictly identical, but rather close to the tests of this potential. And the red curve is the Kooning de la Roche potential. So I did the same thing for lithium 11 plus neutron. Of course, there is no data, but I will use this potential in the next step in lithium 11 plus D as a preliminary calculation. You can do lithium 11 plus D by neglecting the structure and the breakup of lithium 11. So you need a lithium 11 plus N potential. So again, this is compared here with the Kooning de la Roche cross-section. So as you can see, it's not It's much simpler and not very far from the full CDCC calculation. Now let me come on the results on lithium 11 plus D. So the main goal is to investigate both reactions under the same conditions. So the same wave functions, the same optical potential. But of course, it's more difficult because there are many channels, and then the calculations of the coupling potentials take more time. So I couldn't reach a full convergence. So this is more exploratory calculation, and I hope in the future it will be possible to really have a full convergence. So I started here with simple calculation. So assuming that there is no structure on lithium 11. So here I need a proton lithium 11 and neutron 11 potentials. And for that, I use the equivalent CDCC potentials. So there is here only breakup of the deuteron. So you have here the cross-section. These are the experimental points, here the experimental data. And this is the theoretical cross-section. So you see with J max equals 0, so this is J in the deuteron, 2, 4, and I think there is 6. So there is a convergence because this is a simple model, but you can see there is an overestimate of the cross-section here. And then I'm coming to the full 5OD calculation. So this is the convergence with respect to lithium 11. So here the deuteron is in the ground state. So the dashed line is only the ground state. And this is what you get when you increase angular momentum in lithium 11. So as I said before, I couldn't reach a full convergence. I was limited to J equal 2 for lithium 11. So this is the other approach. So lithium 11 is in the ground state, and this is the convergence with respect to the deuteron breakup. So this is a summary. This is ground state plus ground state, this dashed line. This is when you introduce breakup in the deuteron. This is in the lithium 11, and this is when you introduce breakup in both. So you can see that the tendency is okay. There is a reduction of the cross-section around 60 degrees, but you are still far from experiment here. And this is the same in a logarithmic scale. So this is the CDCC calculation. These are the data. And this is the Rutherford cross-section. And the blue curve is obtained with an optical model, which has been fitted by the authors, by Canungo et al. And a surprising result is that these data are rather close to Rutherford. And this is not reproduced by experiment. So here you have the equivalent potential. So the black curves are the CDCC calculations, and the red curves are obtained by the fit of Canungo et al. And here you see that the optical potential has rather short range, much shorter than the CDCC. And this explains why this nuclear interaction means weaker. And this is why reproduces better the cross-section. And I must say this is rather surprising because lithium 11 and deuteron are large nuclei. So we expect the range of the interaction to be large. This is what is found in the CDCC, but this is contradicted by the current experimental data. Okay, so let me come to my conclusions. the lithium-11 structure, this presents 1- resonance at low energies. So this is predicted by many theoretical models, and it was investigated in many other works. But here I check the isoscalar character, which was suggested in this experimental paper, and I could not confirm this isoscalar character. For the lithium-11 plus P for body, there is a rather good description of the elastic cross-section. And breakup effects are important at large angles. And also I've shown that closed channels are important. So the main focus of this work was an extension to lithium-11 plus D, which is a 5-body, and which requires important compute of times, because the calculation of the coupling potentials takes time. There are large coupled channel systems, which means that a full convergence cannot be achieved. By a full, I mean the same type of convergence as lithium-11 plus P. Anyway, the data are surprisingly close to Rutherford, and this would be nice to be confirmed, and maybe at other energies to see if it remains true. Of course, there are limitations. Here we are at rather low energies. This is not common in this field. The center of mass energy is close to 5 MeV, which means that they may have resonances. Also, there are forbidden states in lithium-9 plus P, which are neglected. So this may be a situation where we should pay some attention on the wholly forbidden states. And to conclude, I would say that some data would be welcome. And one of these data is lithium-9 plus P elastic scattering, which would provide optical potential. And also lithium-11 plus P or D data at high energies to see whether this property remains true even at large energy. Okay, I think I'm done, and I thank you.